Well, electrons also behave like waves. De Broglie proposed that particles could have wave-like character in addition to their particle character. And we see this in electron diffraction. And what's really mind-blowing about this is the interference pattern we see, which is much like the interference pattern with light waves, is not caused by two electrons interfering with each other, not caused by pairs of electrons interfering with each other, but by single electrons interfering with themselves. I know, it's disturbing. Because a wave comes to two slits, and a wave can go through both slits at the same time, right? And it gets bent on the other side and interferes with each other. Particles can't do that. So this was electron diffraction. So an electron source shooting electrons at this barrier. And what we observe over here, this is not just a sheet of paper that we're seeing light on it. It's a special sensor that detects the electrons. But we see this pattern of lots of electrons and few electrons, and lots of electrons and few electrons. The same diffraction pattern that we observe with light. So electrons behave as waves. If they were behaving as particles here, some of the particles would hit the slits, they'd go straight through, and we would expect to see just two bright lines. That's what the people expected when they were looking in the box. Well, there's two lines, we'll see two bright lines at the bottom. But that's not what happens. So the wave nature of the electron is an inherent property of individual electrons. And there's an equation known as the de Broglier relation. That's this guy here. The wavelength is inversely proportional to the velocity. Velocity and frequency. Dang, right? That's not confusing at all. This one's velocity, not frequency. I won't try to trick you with that one. This is Planck's constant again. So it's Planck's constant divided by the mass of the electron times its velocity. So we can do problems like this. What's the velocity of an electron that has a de Broglie wavelength approximately the length of a chemical bond? Assume this length to be 1.2 times 10 to the minus 10 meters. So they're saying that that's the wavelength. 1.2 times 10 to the minus 10 meters. And it wants us to find the velocity. This is one where we need to use an equation. And that's the de Broglie relation. The wavelength is equal to Planck's constant divided by the mass times the velocity. So we're trying to find the velocity. So we can rearrange this equation. We can cross multiply. Because you can think of lambda as being lambda over 1. And then you're going to multiply these guys and set them equal to these guys. And then I'm going to solve for V. So I come up with the velocity of this electron is equal to Planck's constant divided by the wavelength times the mass. Well, Planck's constant, 6.626 times 10 to the minus 34 joule seconds. They gave us lambda, 1.2 times 10 to the minus 10 meters. And then we need the mass. This is the mass of an electron. I don't remember what this is. Hey Siri, what's the mass of an electron in kilograms?
Here's an answer from blurtit.com. The mass of an electron is 9.10938188 x 1031 kilograms.
Yeah, she said x10 31 kilograms is x10 minus 31 kilograms. If you look at it, it says it correctly. Why do I want kilograms? Remember when we did all that messy stuff with units with root mean square velocity? Yeah. Kilogram is a base unit in the metric system, and kilograms are involved in joules, and so all the units will work out. So 6.626 times 10 to the minus 34 divided by 1.2 times 10 to the minus 10 divided by 9.11 times 10 to the minus 31. So that's 6.1 times 10 to the 6th. And the units, I mean, we could go through it all, but I don't think anybody's that interested in it. What should the units of velocity be? Meters per second. So that's the velocity of that electron. Any questions? Yeah.
If we have this question, will we be given the mass?
Yes. If this question was on an exam, you would be given the equation and the mass of the electron, either in the problem or on the page of useful information. Yeah, I don't expect you to remember either of those. Any other questions? Well, what about bigger objects? So this says, since quantum mechanical theory is universal, it applies to all objects regardless of size. Therefore, according to the Broglier relation, a thrown baseball should also exhibit wave properties. Why don't we observe such properties at the ballpark? Choice A says, because of the baseball's large mass, its wavelength is minuscule and insignificant. B says, since baseballs don't have a charge, quantum mechanics doesn't apply. And C says, quantum mechanics does not apply to baseballs. Well, what did it say up here? It applies to all objects. So that tells me that these two have to be wrong because they contradict the prompt itself, right? This is the correct answer. The heavier the object, the smaller the wavelength, right? So the electron and light, they have very small wavelengths and their masses are also extremely small. So anything that's big enough to see is going to have an incredibly small wavelength. So yes, the baseball has a wavelength, but it's way too small to detect, okay? So the worksheet that we're doing this afternoon has a couple of things where it's asking you to calculate the wavelength of like a guy who's running the 100-meter dash or something. And we can calculate that, but it's not anything that you'd actually observe. So if we try to observe electrons behaving like wave, then we can't observe them behaving like particles, and vice versa. We talked about the interference pattern as being evidence of the wave nature of the electron, and position, i.e. which slit it's passing through, would be the equivalent of the particle nature. So wave and particle natures are considered complementary, which means the more you know about one, the less you know about the other. So if we take that electron diffraction experiment and which demonstrates the wave nature with the diffraction pattern, and try to trick the electrons by putting a laser beam here, which would detect which of these two slits the electron is going through, then we can't observe the wave nature, we only observe the particle nature, and it behaves like a particle. You take the laser beam away, and you get a diffraction pattern. It behaves like a wave. Yeah. So Heisenberg came up with an equation for this. Of course he did. But basically, the more accurately you know the position of an electron, the less accurately you know its speed, vice versa. So in this equation, which definitely you don't need to memorize that, x is the position of the electron, and so delta would be the uncertainty in the position. This is the mass, and this is delta velocity, so the uncertainty in the velocity. That product is going to be greater than or equal to h over 4 pi. So if this is really small, then that's really big. If this is really small, then that's really big. We can't simultaneously measure the position and the velocity. It's one or the other. So which of these statements best summarizes the uncertainty principle? Both the position and velocity of an electron can be accurately known at the same instant. Either the position or the velocity of an electron can be accurately known at the same instant. Or neither the position nor the velocity can be accurately known at the same instant. Well, it's definitely not A, right? You can't know them both. It's B. You can know one, but then you know nothing about the other. So, classical physics is based on determinacy, which means that the present situation determines the future. You can look at an object and the forces acting on it, and you can predict what's going to happen to it. Indeterminacy means that the future can only be described statistically, because we can't know both the position and the velocity, so we can't predict where this electron is going to go. The best we can do is like a probability map. The electron's probably going to be here. So this is, the classical concept of trajectory. Guy hits a ball goes up and gradually comes down, and this guy on the outfield catches it. When you think about it, it's really, really amazing, because this guy's brain is computing where that ball's going to go. And yet, he doesn't need to know any physics at all. But we learn instinctively what direction the ball's going to go, right? And we can predict that it's going to drop, and we can get under it and catch it. Here we've got the pitcher pitching to the batter, and you can, well, let's say if you put a pitching machine here, right, the ball's going to come the same place every time. If you do that with electrons, they're going to kind of go all over the place, because the situation for the electron now does not predict its future, because we can't know the velocity and its position. So we end up with probabilities. And so there's some concentric circles in here. There's a 20% chance that the electron will be in this innermost circle, 40% chance in this circle, 70% chance in this larger circle, which means that 30% of the time the electron is completely outside that circle. It could hit this lady in the face. Would you notice an electron hitting you in the face? No, you wouldn't. So she's not going to be hurt, but it could do that, right? There's no predicting it's going to go here or it's going to go there.